This video is gonna be a sweet one. I'll explain that in a minute. But first, the raw and unassuming ingredients. Imagine in your experiment you have a sample of size 8, and moreover the variable of interest has an ordinal measurement scale. Still, you'd like to compare an average of your observations against what you expect in theory. Clearly, the assumptions for a t-test are not met, so what can you do? The answer is a sign test. It offers a non-parametric alternative to a one-sample t-test and is one of the simplest non-parametric tests, but also a versatile one. In this video I'll explain how it works and where it can be applied. Your friend really loves wine gums, and while sharing some sweets with you, confesses that she usually eats the green ones first, because these are the sweetest. You can't really discern a difference between the red, orange, green or yellow ones, but your friend is absolutely certain of her case. So you decide to get to the bottom of it and find 10 volunteers for an experiment. You give each of the volunteers a green wine gum and one of another color in a random order. And you ask them to indicate which one of the two is sweeter or whether they are equally sweet. This is a table with results. Each row gives the opinion of one person. If that person thinks the green wine gum is sweeter, a plus is shown in the results column. If the other color tastes sweeter, a minus is shown. And if they are equally sweet, a 0 is shown. As you see, 6 of the 10 people think the green one is sweeter. 2 out of 10 think there's no difference, and the other 2 think that another color than the green wine gum is sweeter. Clearly, the majority of the persons thinks the green wine gums are sweeter. But how much does it tell about what people would taste in general? After all, it's just a small sample that you've drawn. I'm going to explain how you can make a general statement based on this result. First of all, let's consider this category of undetermined cases, the ties. These are not really informative because people couldn't make up their mind. So we take them out of the table. We are left with 8 cases. Let's consider the situation where the green wine gums would in fact taste just as sweet as any other color. This is the null hypothesis for our experiment. And in that case, half of the people would think it's sweeter and another half of people would think it's less sweet. So then you would expect a fraction of 0.5 pluses. And any value higher than 0.5 would mean that the green wine gums are being perceived as sweeter. But wait a minute. We have now translated this problem in one of comparing an observed ratio against a value of 0.5. And there's a test for that, the one-sample binomial test. It gives the probability that you would encounter x successes, or more, in n trials, if the true probability were p. In this experiment, you got 6 successes, in 8 trials, while the probability under the null hypothesis is 0.5. If we calculate this probability, it turns out to be 0.109. So in more than 10% of the cases, you would encounter this result under the null hypothesis. And here we have not even added the possibilities of observing the 2 more extreme cases, where 7 out of 8 or all 8 persons find that the green wine gums are sweetest. If we would add these probabilities, we get a total probability of 0.14 of getting the observed result or more extreme under the null hypothesis. So we do not reject the null hypothesis that the wine gums are equally sweet. In the example, we translated the direction of the difference between 2 observations, not necessarily a numerical difference, into a variable with 2 categories, and subsequently applied a one-sample test for a proportion. It's called the sign test. It is particularly useful for situations where quantitative measurement is impossible, but where ranking the pair of observations is feasible. The null hypothesis tested by the sign test is that the probability that x is larger than y, I, is equal to a given proportion p. Here, x could be the judgment or score under one condition, or before a treatment, and y the judgment or score under the other condition, or after a treatment. Usually a value of 0.5 is chosen for the proportion p, but it can be any value between 0 and 1. You could, for example, test whether x is larger than y in 10% of the cases and set p to 0.1. Finally, you could also replace y with a constant, so that you would measure the proportion where x exceeds a constant. In any of these cases, you would use the cumulative binomial distribution to find the probability of finding your result if your null hypothesis were true. If this probability is small, for example smaller than 0.05, you would reject your null hypothesis. If the number of cases is larger than 35, the binomial distribution can be approximated by a normal distribution, so then the z-test can be used instead. The beauty of the sign test is that you don't have to make any assumptions about the measurement level of your data. It may be ordinal or numerical, and it may also follow any probability distribution. Furthermore, there are no requirements on the sample size, and the power of this test is relatively high for small samples, say fewer than 20 cases. At the downside, the power decreases rapidly for bigger sample sizes. Let me summarize what I've explained in this video. The sign test can be used to test whether a sample quantile differs from a hypothetical population quantile. Testing for a difference in medians and comparing whether paired samples are systematically different are special cases of this more general question. The test statistic in the sign test is the proportion of observations in the sample with values greater than the value specified in the null hypothesis. This proportion is tested with a binomial test when the sample is small and the normal approximation to the binomial when it is sufficiently large. When testing the difference between paired observations, the values or ranks of the pairs can be subtracted and the proportion of negative values act as a test statistic. It's compared with the value of 0.5 under the null hypothesis of no differences between the pairs.